Yeah. For your labs? No, I'd recommend taking notes with a pencil so you can erase it if you need to. And then on your labs, to be turned in, you have to do it in pen. So, and if you do it in pencil, you have to write over your pencil with your pen, which is kind of busy work, but you want to do that, you're more than. But the bottom line is when it's finished, got to be in pen. Okay, so what we're going to talk about today is something called Lewis dot structures. And to understand it, every atom has protons, neutrons, electrons, except for hydrogen, which may or may not have any neutrons. Everything else has got all three of those, plus a bunch more subatomic particles that are kind of wild. But for our class, those are just the three. Okay, the protons, unless we're doing nuclear chemistry, and neutrons don't do any chemistry. What does the chemistry are electrons? Okay, electrons only. And the only electrons that do anything are the outermost electrons and the orbitals. The inner electrons don't. So if we've got a nucleus, it's going to have protons and neutrons in it, except for hydrogen, just has a proton. Buzzing, let's look at lithium. You look on the periodic table up here, lithium is on the top left. So it's got 3 electrons. Now, those electrons are buzzing around the nucleus in a kind of a random fashion, except there are areas that are more densely populated with electrons than others. Now, tomorrow I'm going to talk about the Bohr atom, which was previous to the current quantum mechanical model. But for today, the electrons are, some of them are extremely stable and others are not. The ones that are extremely stable are called core electrons. And they're located in the innermost orbitals. Now, in the case of lithium, there are 2 sets of orbitals. An inner one and an outer one. So the innermost electrons are called core electrons. So those are the electrons, all but the outer one. So since we only have 2 orbitals, that's just going to be the inner one. But if you have something like uranium, there's a whole bunch of orbitals that are core. The outermost orbital, that's called valence. And the electrons in the valence orbital are called valence electrons. Now, the core electrons are very, very, very stable, like I was saying earlier. And the valence electrons are not stable, except if it's full. If it has 8 electrons in it, then they become more stable. Okay, if we start looking at the orbitals, they have up to 7 orbitals. And these are subdivided as well. So if it has just one orbital, it can handle two electrons. Okay, on the second orbital, can handle 8. And the third one is 18, but it's split between 8 and 10. This is 18 and 20. Well, anyway, these get progressively larger. Okay, now for our class, this is the area that's going to be as complicated as it's going to get. We're looking at levels 3 and 4. Now, when you take your next class, they're going to get into 5, 6, and 7. Things get significantly more complex. But you have to have a fundamental understanding of this basic model we're talking about today. Okay, so all the chemical reactions involve valence electrons, not core. So each element has different numbers of valence electrons. So as we go across period 2 or shell number 2, we start with 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, up to 8 valence electrons. And what we like to talk about are if the shells are full, in other words, the valence electrons are totally, and the maximum number, whether it's 2, 8, or 18, that atom or that compound is going to be at its most stable state. So what happens is atoms combine and share their electrons to get to 8. And they call that an octet because there's 8 electrons. But octets only work for the lower numbers. When it gets up higher, the octet can be bigger than octet. Okay, so I like to say full shell. Because the innermost one, the full shell, is only 2. So octet doesn't apply to that one either. It only applies to 2 and 3. And even 3 doesn't work. So a lot of times textbooks will talk about octets. Here we're going to talk about full shell. Full shell means stable. So what we're going to do is we're going to react. Remember I said all the elements in the periodic table except the noble gases are not stable. That's why they react with something else to become more stable. And this is how they do it. What we're going to talk about today. So the idea is we're going to take these valence electrons and combine them with other valence electrons in other atoms to get to 8. If that happens, that's a stable compound. So the idea is to get to that full shell, whether it's 2, 8, 18, 32, etc. Okay, so let me show you what we're talking about here. Okay, this is one of the worksheets on your Unit 2 files on Canvas. on practicing Lewis dot structures. You're also going to be practicing that in lab 12. Now, is that scheduled for tomorrow, lab 12? Okay. So it's perfect timing doing Lewis dot structures today. The lab 12 involves two activities. One is doing Lewis dot structures. The other is doing something called VESPR, which is valence electron pair repulsion theory. A lot of mouthfuls. They always abbreviate it as VESPR. Okay, so what we're going to do today is the main first step for doing that. Okay, what you need to know are these. And now the ones that are particularly important, are those. Now, remember I talked about the periodic table last week, and things are in a group, a vertical column, and the chemistry are the same. So if you look at oxygen, sulfur is underneath oxygen. That means the chemistry of sulfur is like oxygen. And if you look at its valence electrons, look at oxygen, compare that to sulfur. They're identical. That's what makes the chemistry the same, is the valence electrons are the same. That's really important to understand. That means that if I have a reaction with oxygen, I can have the same reaction with sulfur. A lot of organic compounds have sulfur in it. A lot of biochemicals have sulfur in it. Oxygen is used a lot in our body in something called the electron transport cycle, which creates energy. Sulfur can do the same thing. So what's the formula for water? What's the formula for water? H2O, right. So guess what can also form? H2S. And it's very stinky. Sulfur compounds are really stinky. That's what they put in natural gas to odorize it. So when you turn on natural gas, if it wasn't odorized with H2S, you couldn't smell it. Skunks give off sulfur compounds. When things are rotting, things give off sulfur compounds. They're very smelly. Okay, and again, it's because the valence electrons are the same in both of them. Look at nitrogen. What's underneath nitrogen? Phosphorus. Well, let's look at phosphorus. Notice they're the same. Okay, so this is why, and this is real important to understand. This is why chemicals in a group have the same chemistry, because their valence electrons are the same. So okay. Okay, so the reason I call Lewis dot structures is because Dr. Lewis, about 150 years ago, came up with a technique to get a structure out of a formula. So if we look at a formula like let's look at water. H2O does not tell us what water looks like structurally. We know it's got two hydrogens and one oxygen. So let's look at the valence of hydrogens and oxygen. Remember I said, if we can combine two atoms together to get that full shell, we have stability. Water is very stable, one of the most common elements in our on our Earth. We're full of mostly water. We're water animals. Blood is like 99% water. Our lymphatic system, 99% water. We're water animals. Okay, so if we look up here, we're going to find oxygen looks like this. Okay, if we count over from left to right, oxygen's got 6 valence electrons. But look at the way it's set up. We have 4 of them are paired up. And we have 2 of them that are singletons. Now we're going to see tomorrow why sometimes they're paired up and sometimes they're not. Okay, so if it's a pair of electrons, they cannot react further. And there's one exception to that you'll talk about in your next chemistry class. The singleton electrons, though, are unstable. They want to react. So each time we have a singleton, we can react with another singleton to form a bond. Hydrogen has 1 electron, and it's not a full shell, 1 electron. Okay, so this is what happens is the single electron with hydrogen and that one of the single electrons with oxygen can be shared. Now look what that does to hydrogen. How many electrons is a full shell for hydrogen? 2. And look at what hydrogen has now. By sharing that 1 electron with oxygen, it's achieved its full shell. So hydrogen is very happy here. Oxygen, though, is not. It only has 1, 2, 3, 4, 5, 6, 7. Oops. Hi. Okay, not a full shell. However, it can form a full shell by doing the same thing over here. That's why water has 2 hydrogens. Now let's count these electrons again. Okay, hydrogen's got 2, full shell. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen now has a full shell. So oxygen's happy, hydrogen's happy as well. That's why water is so plentiful, is because it's a very stable compound, because all of its bonds are shared to the full shell, hence stability. Now, if we go back up here, you'll notice nitrogen has got 1 pair, 3 singletons. How many bonds do you think nitrogen can have? 3. 3 singletons, 3 bonds. Oxygen's got 2 singletons, 2 bonds. Look at carbon. How many singletons does carbon have? 4. So guess how many bonds carbon can achieve? 4 bonds, 1 per singleton. Now, sometimes we can pair up 2 singletons twice and form a double bond or a triple bond. Triple bond will have 3 pairs of singletons bound together. Okay, these are the steps for forming a Lewis dot structure. Because when we took, going back to water, step one is to put in the middle the atom that has the most singletons. So which has more, hydrogen or oxygen? Oxygen. So oxygen is going to be in the middle. Hydrogens only have one singleton, so they're going to surround the oxygen. That's what step one is. Step two is connect all the atoms together with a pair of singleton electrons. Okay. That's step two. So what we want to end up with is eventually carbon needs 4 bonds, nitrogen needs 3, oxygen needs 2, and the halogens need 1, and hydrogen needs 1. Okay. So oxygen's got 2 bonds, 2 singletons. Number 4. Evaluate each atom as a full shell. If not, move electrons around so that it does. Okay, what's a full shell for oxygen? 8. Okay, does oxygen have 8? We've already shown that. 2, 4, 6, 8. Oxygen. Okay. Verify that each atom has a correct number of bonds. Carbon's 4, nitrogen's 3, oxygen's 2, the halogens are 1, hydrogen's 1. Okay. If four and 5 are met, it's a legal Lewis structure. If not, you got to go back and fix it. You can't have any stray singletons. That's called a free radical. Very, very unstable. So no singletons left unbonded. If 4 and 5 are met, it's a legal Lewis structure. Okay, so it says replace each bonding pair of electrons with a solid dash. So what you do is you rewrite your structure. Notice I left the pairs on the oxygen. It's extremely important. Okay, so what do you guys think? Does this make sense? So what Lewis did, he took that H2O and made it into a structure using these rules. Because they could get formulas for stuff. They couldn't figure out, one, why it was reacting a certain way. They didn't know the structure, and he helped out a lot. Okay, so let's do some more practice here. Carbon dioxide, another stable gas molecule. Why is it stable? Well, let's take it apart. Carbon's got, which is more complex, carbon or oxygen? Which has more singletons, carbon or oxygen? Carbon. Carbon has 4 singletons. So carbon is in the middle. The oxygens are going to be around the carbon. Notice I moved the 2 pairs to the back. So you can move the singletons around as long as you keep them singleton for convenience. Yeah. A non-paired electron. Before you came in, we talked about before you came in, we were talking about that. All right, so we have okay, so that's step one. Step two is we want to attach the singletons together to make a pair. So we have okay. So we have no singletons left over now. Everything's paired up with something. Okay, so does carbon have an octet or a full shell? Remember, each bond has got 2 electrons. So 2, 4, 6, 8. So carbon's happy. Oxygen got 2 bonds, 2, 4, and 2 pairs, 6, 8. So both carbon and oxygen have full shells. Hence, CO2 is very stable. All right, now we're going to redraw that. That's what carbon dioxide looks like. Notice it's a double bond. It's okay to have 2 bonds. It's okay to have 3 bonds. Nitrogen gas. Let's look at it. Okay. Now, when you look at the dot structure for nitrogen, it looks like this. Three singletons. Notice I move the pairs to the outside for convenience. Okay, so that's step one. Step two, connect up the singletons. Okay, do we have any leftover singletons? Yes, we do. We have 2 sets. No more singletons left. So let's count. Each nitrogen now, it's got the lone pair. That's 2, 4, 6, 8. So nitrogen has a full shell and stability. Nitrogen gas, the most prolific gas on Earth. And it doesn't react because it's stable the way it is. Yeah. Because in the second because when we're in shell 2, we can only have 8 electrons total. Shell 3, we can hold 18. And once we get it full, it's very stable because it acts like a noble gas. Noble gas is very stable. Why are they so stable? Because they have full shells. Full shell. Okay, so that's an example of a triple bond. All right. If we look at problem 3 here, C2H5OH formula. Now you can have multiple Lewis structures that are legal, just fine. For example, this guy, I said draw 2 structures. By the way, your next test is going to be Tuesday. You'll cover Lewis dot structures, I'm not sure we're going to get to nomenclature, maybe in test 3. It's kind of a, this question was nomenclature. Um, on Thursday, I'll tell you what to study. We'll also go over a practice test on Monday. Okay, all right, so okay, C2H5OH. And by the way, this is called drinking alcohol, ethanol. Okay, it's also called dimethyl ether, which is an analgesic used to be used for major operations where they had to put you down. This is what they'd use. Okay, now there are 2 versions of this that are legal, 2 Lewis structures. So let's do those now. Okay, so carbon, hydrogen, oxygen. Carbon has the most singletons, so it goes in the middle. And we have 2 of them. We have 6 hydrogens. We're just going to run those around the outside. And we also have an oxygen there. Okay, so that's step 1. Step 2, connect everything up with a single bond. Now, what's wrong with what I've done? Yeah. I left something out, didn't I? The oxygen needs to be part of it. And I have no bonds over to oxygen. So we need to change some of these bonds to include oxygen. Well, let's hook up the oxygen. Okay, what do we do now? Yeah. I mean, instead of connect, but then the oxygen wouldn't be connected to the carbon. We have 1 singleton left over, right? On the oxygen. You see what? Okay. Okay, so the carbon also has a singleton. So we got to clear these singletons up. We cannot leave them unbonded. Okay, one way to do it is, well, let's do this. And then we have a singleton left over in the oxygen, right? So what we're going to do is we're going to move the hydrogen over on the other side of the oxygen. There. Now, do we have any singletons left over? No. So drinking alcohol is a stable compound. And this is what it looks like. This is called, the fancy name for this is called ethanol. Okay, so we have 1 legal structure, but I said you have to do 2. So we have to scrounge up another combination. Now, moving this around like this does not mean it's a new structure, because atoms and molecules are constantly tumbling in space. They're moving like this, they're stretching, compacting, tumbling, moving from one location to the other. Unless you're at extremely low temperatures, it's called absolute zero. Other than that, everything's moving. So if we flip this over 180 degrees, it's still the same molecule. Okay, so let's go over here. Okay, instead of starting with carbons in the middle, let's start let's put oxygen in the middle. That let's notice I moved the electron pairs around so it's more convenient. That's fully fine to do. Okay, then we have 6 hydrogens total. Okay, so let's connect up the singletons. Okay, do we have any leftover singletons? No, we've all got them connected up. Okay, we have octets on everything. Carbon's got 2, 4, 6, 8. Oxygen's got 2, 4, and the 2 lone pairs, 6, 8. Carbon's got 2, 4, 6, 8. Carbon's got 4 bonds, oxygen's got 2, hydrogen's got 1. So it's a legal structure. Yeah. Everything in shell 2 over here, periodic table. Starting with lithium on the left, and you go across. They all need an octet on your periodic table. And if you do that, I'm sorry? Yeah. Yeah. I mean, yes, in period 2 or shell 2, a full shell is 8 electrons or an octet. Okay. We're not quite finished with these guys. Okay, and this is called dimethyl ether. And don't worry about memorizing those names. I just want to give you the name of it. And they're very, very different compounds. Same formula, different chemistry. So as a chemist, you come up with these 2 structures. Which one is it? So you have your compound, and then you test that. Is it an alcohol or is it an ether? And you run tests to determine that. That could be running it through an instrument, could be doing wet chemistry on it.
What's the difference?
What-
Alcohol.
They're just not connected the same way. So the chemistry is not the same. Now, who's heard of a breathalyzer? Okay, gosh, all your hands are going up. If you had in your mouth dimethyl ether, that breathalyzer would give you a negative test because ethanol is a primary alcohol and it oxidizes really easily. So in that breathalyzer, there's a little chemical reaction going on between the ethanol and what happens is it oxidizes it. And there's a little chemical that changes color. The more intense the color, more alcohol. And they calibrated it. That's how it works. The last time I was on jury duty was over a DUI. And one of the lawyers who was, selecting jurors asked my profession. I said, I'm a chemistry professor. And he goes, do you know how a breathalyzer works? I go, sure. And he says, do you know how to beat it? I said, yes, I do. And then the judge stopped me and cleared the courtroom. Everyone except the DA and the defense attorney, judge and me. And because the judge did not want me explaining how to defeat the breathalyzer to the whole courtroom. And I explained how it works. You just take Listerine mouthwash. When he's stopping you, gargle, spit it out, and it'll go off the charts, meaning that there's no way that breathalyzer can detect ethanol in your breath with all that Listerine there. So a lot of people, particularly back in the 60s, would carry mouthwash in their glove compartment, Listerine. That is half alcohol. That's how it kills the germs in your mouth, because it's half alcohol. And I got excused off the jurors list by the defense attorney. Okay, so the last step on this is to take the little circled bonds and make them into lines. Oops, let's see there. So this would be a final structure. And that's what that would look like. Okay, now you need to practice this a fair amount. So that's what we're going to do today for the rest of the hour here. Okay, so go ahead and do some of these, because you do have to practice this. In lab 12, you'll have a fair amount of practice with dry lab 12 as well. Let me see how you're doing here. On the surface, he's looking pretty good. They'll just go anywhere around the P.
Oh, okay, so it doesn't have to be like they don't have to be together.
They have to be together though,
Oh,
but the pair can be anywhere around
okay.
them.
So like this.
Yep, exactly. And now you need to put, right, all three pairs around.
So this is fine.
Yeah. S is underneath oxygen. Right here, oxygen, sulfur. Now, problem with sulfur, it's in shell 3. Shell 3 can have more than an octet and be okay.
Okay,
So notice, see, oxygen's fine. It's
Yeah.
got
8.
2, 4, 6, 8. This has got more though.
Oh, yeah.
And there's the 2 electron pairs as well. So what happens with sulfur is, see, it's got 1, 2, 3, 4, 5, 6 valence electrons. But what happens is it taps into these down here. So that's why shell 3 and beyond can have more than 8 electrons.
Oh, it's just a. What you mean by plus 10?
Yeah. And the 10 are in here.
Oh. Okay. Question, like so you see how this one has, like, hydrogen has 1 valence electron, and sulfur has 6 valence electrons. So when it says number of valence electrons, what do I get?
Well, it's a total of 2, 4, 6, 8.
So I write 8.
No, 8, and then 1. Let's let me back up. 6 electrons for the sulfur, and then 1 electron apiece for the hydrogen.
Yeah.
So 6 plus 1 plus 1 is 8.
Okay. So number of valence electrons.
Yeah, it's gonna be like fluorine. So we have 8, 6, and 6. So 14.
8, 6, and 6 is 20.
There's 8 here, right? And then 6 and 6 left over.
Yes, 20, right?
Yeah. And don't worry about doing anything with S in it.
Okay, so we got the next possible.
Hmm?
We got next possible.
Yeah.
Okay.
With H2CO2. Would that work?
Yes, except yeah, shoot her hand up for you. Let me help her. I'll be right here.
No, you can help.
Okay. She's just being nuts.
Oh, okay.
Okay, so let's start over on this one. Okay, start with a C here and have 4 singletons around it.
Oh, you only want 4.
Yeah. Right, okay. Then put oxygen over here. Okay, and it's got 2 pairs and 2 singletons.
And then,
And 2 singletons. That's the 2 pairs, and right,
yeah, and then like that?
1 more. Yep. But they're not together though, they're single.
Oh,
See, these are paired. And the paired ones don't form a bond, but the single ones do. So they have to all,
oh,
that's why carbon can have 4 bonds because it's got 4 singletons. Oxygen's got 2 singletons, that means it can form 2 bonds. The pairs, they're already 2 electrons, so it can't bond anymore.
so you wouldn't do, I know this is like to represent 2 electrons connecting.
2 singletons coming together to form a bond, yeah.
So
Okay, but I'd like you to start with just the dots all over the place.
the dot.
Do the lines last. After you know it's a legal, see on this one how I waited till the very end before I wrote that?
Yeah, so this one is the same as this. The C2H5OH.
Yes.
Or
Okay, so
Mhm.
so erase those two close together and make them single, two singles.
Two singles?
Yeah.
How do you do that? You go like that, and then,
And then put another one below it, but not as a pair. They're separate. See, oxygen has 1, 2, 3, 4, 5, 6 valence electrons, but 4 of them are paired up. So you only have the remaining 2 are singletons. And the only way you can form a bond is between 2 singletons. Okay. All right. So do the same thing with oxygen over here. Put the pairs on the outside, the singletons in the middle. Yeah, just like that. Okay. And now we have 2 hydrogens to deal with.
I just
Yeah,
go here.
that's fine. Put the dots on the hydrogen.
On the hydrogen.
Yeah, it has a single dot. Why don't you put it on the other side? So when you draw the little line that are all together, and you can leave it the way it is, but let me show you.
So
Yeah, so if you do it like this, when you try to connect that to that, it's kind of goofy. You have to kind of go like that. But if the dot was over here, see how much easier it would be? Just go like that.
okay.
Okay. Now we need to connect up everything with a single bond. That means 2 singletons come together to form a bond. So we have 1 singleton, 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 singleton.
So then it would turn out like that.
No,
No?
no, it's just
Oh, okay. Wait, what am I doing?
the next thing. After you get this set up like
Uh-huh.
this, then you connect everything up with 1 bond. In other words, 2 singletons forming a bond. I need to go turn off the recording. Just see if you can figure that out. I'll be right back.